All right, hey everyone, and welcome. If you're gearing up for your WAEC, JAMB, or NECO exams, you are in exactly the right place. In this tutorial, we're going to break down radioactivity and nuclear chemistry so you can totally ace it. Let's jump right in. So, what's the connection here? Well, the answer to all of them is radioactivity. I know, it might sound super complex, but this one single concept has some incredible world-changing applications, from figuring out how old dinosaur bones are to generating clean power and even fighting cancer. We're going to make it all make sense. Okay, first things first, we have to start with the foundation. So, what on earth is radioactivity? Let's get right to the core of it. To put it simply, radioactivity is just what happens when an atom is unstable. It's got too much energy and it wants to calm down. So, it spontaneously shoots out some of that energy as radiation. This whole idea was first spotted by Henri Becquerel way back in 1896, and then the amazing Marie and Pierre Curie really dug into it. So, why are some atoms unstable in the first place? Well, it all boils down to the delicate dance between protons and neutrons inside an atom's nucleus. If that ratio is off, if there's an imbalance, the nucleus gets shaky. It becomes radioactive. So, when that unstable atom lets off energy, that energy comes in the form of radiation. And for your exams, you absolutely, positively have to know the three main types. So let's meet them. First up, we've got the alpha particle. Just think of this guy as a tiny helium nucleus that's been shot out. 2 protons, 2 neutrons. That means it has a positive 2 charge. It's kind of the heavyweight of the group, but it's also a bit of a slowpoke. It has really low penetrating power, so low that a single sheet of paper can stop it cold. Next on the list is the beta particle. This one's basically a super high-speed electron. And since it's an electron, it's got a negative 1 charge. It's way smaller and faster than an alpha particle, so it can punch through a bit more. You'd need something like aluminum foil to stop a beta particle. And finally, the big one, gamma radiation. Now, what's wild about gamma is that it isn't a particle at all. It's a high-energy wave. Basically, pure energy. No mass, no charge. And because of that, it's an absolute beast when it comes to penetration. It can slice through paper and aluminum like they're not even there. You need thick blocks of lead or concrete to stop gamma rays. Okay, this table right here, this is your exam cheat sheet. Seriously, memorize this. You can see everything side by side. Alpha, the big positive particle that's stopped by paper. Beta, the small negative particle stopped by aluminum. And gamma, the neutral super powerful wave that needs lead. Got it? Good. All right, now that we know the players, alpha, beta, and gamma, let's dive into the bigger concepts. We're going to look at the powerful nuclear reactions and the number one way we measure how they decay over time. You are going to get asked to compare fission and fusion. It's actually pretty simple. Just remember, fission means division. Think of a big, heavy nucleus like uranium-235 splitting apart. That's what happens in nuclear reactors. Fusion is the opposite. It's about combining or fusing things together. It's what powers the sun, with tiny hydrogen atoms slamming together to become helium. Now, for a topic that is pretty much guaranteed to be on your exam, half-life. It's exactly what it sounds like. It is the specific amount of time it takes for exactly half of a radioactive sample to decay into something more stable. And the key thing is, this time is a constant. It's like a unique fingerprint for every single radioactive isotope. And here it is, the formula you've got to know by heart. N is the amount you have left, and naught is the amount you started with. Lil t is the total time that's gone by, and capital T is that special half-life time. If you can master this formula, you can solve just about any half-life question they throw at you. Okay, enough theory. It's time to put this into practice. The real test is seeing if you can apply this stuff. So let's walk through some actual past exam questions step by step so you can see exactly how it's done. Have a look at this. This is a classic WAEC question. We've got the half-life, that's T. We've got the initial amount, that's N naught. And we've got the total time, that's T. So how would you even begin to solve this? Let's break it down together. First step, figure out how many half-lives have actually happened. We take the total time, 12 days, and divide it by the half-life of 4 days. That gives us 3. So 3 half-lives have passed. Now we plug that into our formula. We take the initial 160 and multiply it by 1/2 to the power of 3. Well, 1/2 cubed is just 1/8. So 1/8 of 160 is 20. Simple as that. Now, here is the number one trap that students fall into. They think the decay is linear. They'll try to subtract the same number over and over, but it's not. It's exponential. It halves each time. So after one half-life, 160 becomes 80. After the second, 80 becomes 40, and after the third, 40 becomes 20. It's a curve, not a straight line. Don't forget that. Okay, ready for another one, this time from JAMB. Now pay close attention to the wording. Notice that key word fraction. That's a huge clue that tells us this problem is actually going to be a little easier. See, the process is even simpler. First, we do the same thing, find the number of half-lives. So 30 years divided by 10 years is 3. 3 half-lives. And since the question only wants the fraction that's left, we just need to calculate 1/2 to the power of 3, which is, you guessed it, 1/8. And we're done. And that leads us to a fantastic pro tip that'll save you precious time in the exam. If you see the word fraction in the question, you can completely ignore the initial amount. You don't need it. The answer is just 1/2 raised to the power of the number of half-lives. It is a brilliant shortcut. Whew, we have covered a lot of ground. So before we wrap this up, let's do a super quick final review of the absolute must-know points to lock in for exam day. Okay, here's the final checklist. First, know those radiation charges cold. Alpha is +2, beta is -1, gamma is 0. When you're balancing those nuclear equations, make sure the top numbers and bottom numbers add up on both sides. Watch your units, don't get tripped up between days, hours, and years, and remember the easy stuff. Fusion happens in stars, fission happens in reactors, and if you have time, practice sketching out those decay graphs. All right, it's time to put what you've learned to the test. Here is one final problem just for you. Go ahead and pause the tutorial, work it out using the steps we covered. You know how to do this now. How many half-lives pass? What's the final calculation? You have all the tools you need now. Radioactivity isn't some big mystery. It's a topic with clear, predictable rules. If you practice these problems and remember these key concepts, you're going to be in a fantastic position to crush this section of your chemistry exam. You have got this. Good luck! That's it for today. Great job following along. If you found this tutorial helpful, don't forget to subscribe to our YouTube channel for more easy-to-understand lessons. And hey, want to practice more questions and get step-by-step solutions? Visit ExamKP.com right now and keep learning smarter.